Hello everybody and welcome. In this video we are going to look a little bit more at electron configurations. We're going to review on how to do write electron configurations, specifically the orbital diagrams, and we're also going to cover the noble gas configuration. So let's do a quick little review on the rules that we have to follow when following electron configurations. Remember, we have the Aufbau principle. We have the Pauli exclusion principle. And we also have Hund's rule. Now, the Aufbau principle, think of that as filling a glass of water. We always fill our glass of water from the bottom and then work our way up. So we are always filling the lowest energy levels first. All right. With the Pauli exclusion principle, that simply is that no two electrons can have the same four quantum numbers, which means that electrons in the same energy level and orbital and orientation must have opposite spins. More specifically, one up and one down. Now, we went into more in-depth notes when we talked about this, and the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. But this simply is this. We're just reviewing these notes pretty quickly and going from there. And with Hund's rule, we say that in an orbital, in a specific orbital, you must have one electron in each orientation before you can go back and double up. Okay, so now that we've covered these rules, let's take a look at doing an example of an electron configuration. So let's first start off with a nitrogen. Now, nitrogen has an atomic number of 7. Okay. Now, this means that it has 7 protons. And we are assuming that all of these are neutrals, so because of that, it also has 7 electrons. And because we are talking about electron configurations, the electrons are what we care about. So, remembering our memory A diagram from class, in the first energy level, we have an s orbital. In the second energy level, we have an s and we have a p. In the third energy level, we have an s, we have a p, and we have a d orbital. The fourth energy level, we have an s, we have a p, we have a d, and we have an f orbital, so on and so on. Oh, I'm sorry. That would be a 5p, 5d, 5f, so on and so on. And when operating with this memory A diagram, we always go on the diagonal. So we start here and then work our way down. And when we reach the end of an arrow, we go back up to the beginning of the next. So this is the pattern that we will be following when we're writing orbital diagrams. So let me get those red lines out of there. They just kind of make it a little bit messy. So let's start writing our orbital diagram. Let's see, orbital diagram. What we start out with first is the lowest energy level following the Aufbau principle, the 1s. Now an s orbital only has one orientation, so we only put one line above. We're going to fill that orbital according to the Pauli exclusion principle with one arrow up and one arrow down. Those are to represent the two electrons with opposite spins. Okay, we've just covered the first energy level. Now we're going to go up to the start of the second arrow and go down from there. So the next one we will encounter is the 2s. Again, we fill up one and down one. From the 2s, we then go to the 2p. Now, the p orbital has three orientations, so we're going to draw three lines for that. And according to Hund's rule, we fill one in each first, and then we can go back and double up. But before we do that, let's take a total count of our electrons. We see we have 2 there, we have another 2, and so far we have 3. Adding these up, we get 2, 4, and 7. And in fact, 7 electrons. That is what we wanted to end with. We have our 7 arrows representing our 7 electrons, and we are done. This is our orbital diagram for nitrogen. Now, if we were to write a longhand diagram, or excuse me, the long form of the electron configuration or the electron configuration without the arrows, it would be very similar. The only difference would be is that instead of arrows, you would have superscripts, and it would look like this. You would have a 1s2, a 2s2, and a 2p3. Notice the 1s, the 2s, the 2p all remain the same. The difference is instead of arrows, we have superscripts. When we have 2 arrows, we write a 2 for a superscript. Those small numbers represent the number of electrons. All right, let's continue on. We're still going to have our memory aid diagram up here. We're going to use that. Let's get something a little bit more difficult. Let's jump right in, and let's do arsenic. We're going to do arsenic. Elemental symbol AS, atomic number 33, which means we are looking to fill 33 electrons. All right, following our memory aid diagram, we're going to start with the 1s. I'm going to do the orbital diagram. Then we move to the 2s, one up, one down. Then we move to the 2p. Remember, those 3 are part of the p, and we're filling this according to Hund's rule. One up, one up, one up, one down, one down, one down. After the 2p, we then move to the 3s, one up, one down. From the 3s, we move to the 3p, up, 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 down, down, down. I'm going to get that little dot out of the way. It's going to be a little confusing. From the 3p, we then move to the 4s. And after I write the 4s, I want to actually just take a moment to count our electrons. So we see we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So as of this point, we have 20 electrons accounted for. We still need 13 more to go. After the 4s, we then can go to the 3d. Now, this is our first time filling a d orbital. Remember, a d has 5 orientations. And we're going to fill that in the same way. One up, one up, one up, one up, one up, and then one down in each of the orbitals. This now brings us to 30, and we're looking for only 3 more electrons to complete our orbital diagram for arsenic. I'm actually just going to put it right at the end. I'm going to slide over just a hair. And after a 3D, we then fill a 4P. So these 3 right here are the 4P. Remember, we only need 3, so one up, one up, one up. And we have just completed the orbital diagram for arsenic. Okay. Again, if we were to write this in the long form, we would just replace the arrows with exponents. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p3. All right, so that is how you do the electron configuration for orbital diagrams and the longhand. The next thing I want to explain to you is a little bit about noble gas configurations. And to do noble gas configuration, what I'm actually going to do is we are going to erase part of this. We're going to keep our memory aid diagram because that is a very good thing to have. We are going to delete all of this, keeping our memory aid diagram, and we are going to now try yet another electron notation. But we are actually going to do the electron notation for xenon, Xe. Now, Xe is pretty daunting. It has 54 electrons, but I know you can do it. So instead of drawing the orbital diagram, what I'm actually going to do is just do the longhand. That way we don't have to draw all these arrows. So it is going to be a 1s2, a 2s2, a 2p6, a 3s2, a 3p6. Just so you're following along, what comes after a 3p6? Correct, that is a 4s2. From there, we then go to a 3d10. From there, we continue on to a 4p6 and a 5s2. From a 5s2, we move on to a 4d10. From there, we go to a 5p6. All right, let's just do a quick count to see how many electrons we have. Hopefully you're counting, and I will be counting as well. All right, we're actually very fortunate because this ends us on 54. Oops. 54 total electrons. So this is the longhand notation for xenon. 54 total electrons. Now you could see why if we did this as an orbital diagram, it would look very messy. It would take up a large deal of space. So we just kind of did it shorthand. But I know you guys would be able to do this as a long form. Just remember, it would be the 1s, 1 up, 1 down, the 2s, 1 up, 1 down, so on and so on. All right, in our efforts to explain a noble gas configuration, now I think the next element that we want to write down is barium. So now we're going to do barium. Okay, barium is Ba. It has 56 electrons. So we're going to continue on and write the longhand form for barium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. I've run out of room. This we know because we just actually wrote this for xenon is 54 electrons. We only need 2 more. After a 5p, we then, oops, I apologize, guys. I apologize big time. I'm going to have to make a quick adjustment. Just bear with me for 1 second. I'm going to move this up. And when I do that, I'm going to add in our next energy level because this green arrow actually falls all the way down to a 6s, 6p, a 6d, a 6f. So I am just going to adjust these slightly. This arrow comes down, this arrow comes down, there's another arrow here, so on and so on. So after the 5p, we then go to a 6s. All right, so let me continue with that, and I'm just gonna kind of ran out of room there, so I'm gonna write that right here as a 6s. We needed 2, it's a 6s2. Now there's something I'd like you to pay attention to, and if we look at this, we see that all of this right here is written right here for barium. So what actually happened is we just rewrote xenon with adding a 6s2 on the end. When looking at the periodic table, I'm going to do my best to kind of fast hand draw this. When looking at the periodic table, right, these elements right here, doesn't go all the way down to the bottom, but these elements, helium, neon, argon, krypton, xenon, and radon, these are called the noble gases. And we call them the noble gases because their outermost energy levels are filled. Every time we've reached one of these gases, we always go over and start a new S, whether it's a 1s, a 2s, a 3s, a 4s, a 5s, a 6s, or a 7s. And for this reason, we can use these electron configurations as kind of a shortcut. So what we will do, to replace an electron configuration for a noble gas, we actually write it in brackets. So if we look to our previous example for barium, right here with barium, we had xenon's noble gas configuration written out, and then we put on a 6s2 to finish it. So what we would actually do is write xenon in brackets. By writing xenon in brackets, we have just covered that entire configuration. All that's left to do is continue with a 6s2, and we now have the noble gas configuration for barium. There's a couple rules here, just two rules. When looking at the periodic table, you need to make sure that you use the noble gas that comes before your element. All right, so let me bring up a periodic table here. So looking at this periodic table, if we were to pick, say, scandium, you can see my mouse pad right here. Actually, let's pick an easy one. Let's look at magnesium. If we were to pick magnesium, we're going to go to the noble gas right before it. So that would be neon. We would put neon in brackets. If we were to pick germanium, we would go to the noble gas that comes before it, which would be argon. Argon would go in brackets. If we had francium, Fr, way down here, we would go to the noble gas that comes before it. I'm just going all the way down the line and going up. That's radon. Radon would be in brackets. What about lithium? All the way over and then move up. Helium would be in brackets. Same thing with fluorine. Over and up. Helium would be in brackets. Now, that explains what to put in brackets, but how do we then explain what to start with? Do we start with a 1? You will always start with an S, but is it a 1s, a 2s, a 3s, a 4s, a 5s, a 6s, or a 7s? Well, that's pretty easy to figure out. Let's take, for example, bromine. The noble gas in brackets will be argon. Now, to figure out where we start, we're going to look to the row that bromine is in. It is in row number 4, so we start with a 4s and then continue from there. If we're looking at barium, the noble gas that will be in brackets will be Xe, xenon. And we will start with a 6s. So let's do 1 or 2. That way we can kind of figure out and make sure we're getting this right. Let's see, I'm going to do a little bit of erasing here, just so we can keep our memory aid diagram up. All right. So let's start off with, let's do sodium. Now, the noble gas in brackets, find sodium, it is 11. If we go all the way to the end of that, we see argon, and then we go up one. So the noble gas that is in brackets would be neon. And then how do we know where we start? Well, sodium is in the 3rd row, so we would start with a 3s. So that means we are starting right here, guys, starting right there. So we would have a 3s2. Oh, excuse me, I apologize. One thing you want to make sure is you want to count your electrons. Neon has 10 electrons. We ultimately want to get to 11, so we just need a 3s1. If we were to write this as an orbital diagram, it would be Ne 3s with 1 up arrow. Let's try another one. Let's try maybe, how about sulfur, S. Sulfur has 16 electrons. The noble gas that comes before sulfur, again, is neon. Neon, we remember, had 10 electrons, so we need to account for 6 electrons. Sulfur is in the 3rd row, so we will start with a 3s. 3s, 1 up, 1 down. We still have to find 4 more electrons. After the 3s comes a 3p. We go up, 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 and then 1 down. This is our noble gas configuration, both as the shorthand and the orbital diagram combination for sulfur. All right, let's try one more. Let's make it more of a difficult one. Let's actually take advantage of that noble gas. Let's try tin, SN. We're going to do tin. Tin has 50 electrons. The noble gas that comes before tin is krypton, Kr. By putting Kr in brackets, we have accounted for 36 electrons. So now what we need to do is find essentially 14 more electrons. Looking at tin, we see it is in the 5th row, which means we are going to start with a 5s. 5s, 1 up, 1 down. From a 5s, we then move up to a 4d. Remember, a D has 5 lines. And we are going to fill 1 up, 1 up, 1 up, 1 up, 1 up, 1 down, 1 down, 1 down, 1 down, and 1 down. Now remember, we needed to find 14. We've accounted for 12. After a 4D comes a 5P. We only need 2 more, and that is it. We are done. We have just successfully written the noble gas configuration for tin. Kr 5s2, 4d10, 5p2. Please remember that we haven't done any examples here, but when you do get to an f orbital, you have 7 lines with a maximum of 14 electrons. I hope this has helped you guys in figuring out electron configurations and noble gas configurations and orbital diagrams. Good luck, and I wish you guys all nothing but the best. Take care. This is Mr. F saying, have a great day, everybody, and chemistry rocks. Bye, everybody.